My name is Richard Dedekind. I lived from 1831 to 1916. I would like to introduce you to a new, constructive, proof of the main theorem of the Galois theory. We will prove that theorem in two new ways. That theorem, as is known, deals with the one-to-one relationship between the subgroups of the Galois group and the intermediate fields of the corresponding Galois extension. But first we will prove that a Galois extension always has a primitive element. That is a crucial step in this proofs. For this, we use the first memoir of Galois. Here you see a picture of the important lemma 2 from that 1831 memoir, as printed, in the well-known book by Peter Neumann, in which all the writings of Galois are included. This memoir is published in 1846, in the journal de Louville. Among other things, Galois gave no proof for this lemma. I proved these lemma in the lectures on Galois theory, that I gave as a private tutor in Göttingen in the winter semesters of the academic year 1856 to 1857, and the academic year 1857 to 1858. Afterwards, I took notes of those lectures, and they were published in book form not so long ago. I was probably the first to lecture on Galois theory. Only 4 students attended the original lecture, including P. Bachmann. He wrote to me afterwards, that he thought everything was very new, but that he had understood little of it. Lemma 2. Given any equation with distinct roots, a, b, c etc., one can always form a function v of the roots, such that no two of the values one obtains by permuting the roots in this function are equal. For example, one can take v equals a plus b plus c etc. a, b, c etc. being suitably chosen whole numbers. Let L, a field extension of K, be a Galois extension with degree n. Then there is a polynomial f, from Kx, with different roots, and each with multiplicity 1, such that the field L, is the splitting field of the polynomial f. Take the roots of f, in lemma 2, then v is a primitive element. Because the minimum polynomial of v has n roots. Galois also writes a third lemma. Let's see it, because it follows directly from the above. Lemma 3. When the function v is chosen as indicated above, it will have the property, that all the roots of the given equation, can be expressed, as rational functions of v. This follows from the fact that v is a primitive element. Galois gives a very different proof. We are now going to provide a proof for Galois lemma 2. I will do that by proving 2 lemmas. The proofs can be found in the German book edition of my notes from the lectures in Göttingen. The book was written by Winfried Scharlau in the year 1981. Lemma 1. If any whole rational function of any number of variables, with certain coefficients is given, which does not vanish identically, then one can always assign to the variables such integer numbers, for which the function contains a value other than 0. The proof goes by induction to the number of variables. You can read it in the picture below. Lemma 2. Denoted by R1, R2. Rm, a series of m different, real or complex, numerical values, then there are always m integer numbers, alpha 1, alpha 2, alpha m, for which the sum of the products assumes different values, if one performs all possible permutations of the R1, R2, Rm. The proof goes by using lemma 1. We first define the sum function S, using a permutation sigma, of the permutation group. Then we make the product function of the differences. The differences are not 0, so that the product function is also not 0. We apply lemma 1 to the product function. You can read it in the picture below. We now give a first proof of the fundamental theorem of the Galois theory, using the proof as given by Artin. We are going to rely on the presence of a primitive element. I would like to ask you to provide the evidence yourself as good practice. Soon I will make you familiar with an article where everything is written out. The starting position is above. Definition 1 shows how Emil Artin adds a field to a group H. In definition 2 we explain how we do this. We use the symmetric polynomials. Although the definition depends on alpha, the same field is obtained with another primitive element. If we prove proposition 3, then we know that the set in definition 2 is a field. And again, that it doesn't matter which primitive element we take in definition 2. In proposition 3, one direction may be difficult. Use the arithmetic mean formula. At proposition 4, the minimum polynomial of alpha has as zeros the images of alpha. Under the action of the automorphisms of the group H there are exactly m. In proposition 5 you must apply the fundamental theorem of symmetric polynomials. The coefficients of the minimum polynomial of alpha mentioned at proposition 4 are exactly the values of the elementary symmetric polynomials, in which the values are filled in, which are obtained by applying the automorphisms of the group H to alpha. We will now prove the fundamental theorem of the Galois theory, by using the fundamental theorem of symmetric polynomials. Our proof now also comes to rely on the primitive element alpha. Again, I would like to ask you to provide the proofs yourself as a good exercise. The starting position is above. At proposition 1, the coefficients of the polynomial f mentioned there are exactly the values of the elementary symmetric polynomials, in which the values are filled in, that are obtained by applying the automorphisms of the group H to alpha. At proposition 2, in this proposition, the main theorem of the symmetric polynomials is used. At proposition 3, we use that every automorphism from H is the identity on F. If we combine the three propositions, we conclude that we can also put an equal sign in proposition 2 and proposition 3. Proposition 2 guarantees the surjectivity, and proposition 3 guarantees the injectivity. This proves the main theorem of the Galois theory. In the above two proofs the main theorem of the symmetric polynomials is always used. Artin's proof uses the Artin-Dedekind's lemma. So there is always a difficult component in a proof of the main theorem of the Galois theory. Charlas writes in his book that there is still a second manuscript of my hand, from which he concludes that I have dealt with the history of the fundamental theorem of symmetric polynomials and that I would be looking for a new proof. That second manuscript is not in the book. There is also an Italian book that is about my manuscript. A portion of my manuscript has been photographed in this book. The book is written by Laura Torti Rigatelli in the year 1990. As far as I know there is no English translation of Charlas's book. A translation might make my manuscript more accessible. As known, an English translation of Galois' first memoir is in Harold Edwards' book on Galois theory. In the German book by Heinz Lüneburg, the second part, the first memoir of Galois is discussed, and also my lectures on Galois theory, that I gave in Göttingen. Among other things, the above-mentioned lemmas are proven. Lüneburg also provides a lot of historical information. The proof of the main theorem of the Galois theory given here can be read in this article. Finally, as you now know, the main theorem of the symmetric polynomials and the main theorem of the Galois theory can be derived from each other. As is known, the main theorem of algebra can be derived from the latter theorem. I hope you have enjoyed my presentation, and thank you for your attention.
Bonjour, je suis Evariste Galois. J'ai vécu, de 1811 à 1831. Ce que je vous recommande fortement, c'est de lire non seulement les travaux des mathématiciens du temps présent, mais aussi les travaux des mathématiciens du passé. Rappelez-vous, Emil Artin a dit. En principe, tout est déjà dans le travail, de Richard Dedekind.